friends? I'm Sharky, and I got another project on the bench. This one's a doozy. It's what we, in the industry, we call this one, very technical term. This one's a doozy. This box here comes from Mr. Nationwide Good News, and it's got a bit of a history. I don't remember every detail, but I know that Mr. Nationwide Good News hit me up, probably 2.5 years ago to take a look at this box. And I wasn't able to do it because I was moving out of my old home and I wasn't going to have a place to work on it. So I said, hit me up in 6 months. 6 months from now, give it a shot. Maybe I'll be ready. Well, I wasn't. And that happened a few more times while I'm working on my house and getting my shack set up. He wanted me to work on it and I wasn't able to. So it sounds like, the long story short is that this box blew up and he sent it to somebody to work on it and then got it back and then it blew up again. And I think that happened twice, maybe more. Just taking a look at it, I don't wonder why. I see issues just about everywhere. So these LDMOS FETs here are BLF 188s. They're not the biggest or the baddest, but if you get them set up properly, they do the job. Let me bring the camera over here and you guys can see what's going on with this. So there's quite a few things that stand out to me. I'm not going to say any one of them is the reason why this box blew up. But there's just stuff like this, coax with the shield not connected, sitting there, dangling out in open space. The gobs of hot glue, those are a nice touch. You think there's enough ferrites on that fan wire? I mean, I understand the problem of RF getting into your fans, but I don't think any more ferrites is going to help that situation, considering the RF is coming straight from the pallet and going straight up into the fan wires. Most likely, anyway. But there's lots of weirdness in here. Lots of it. One of the bigger red flags is stuff like this, when you see coax just kind of stripped way back and all that exposed coax just radiating RF into the box. One of many red flags. It's got these, what is that? A hybrid combiner and some kind of splitter. I haven't looked at it very closely to see how it works, but those, I wouldn't use those just because the ones that I make, I know that they work and they work flawlessly. So I wouldn't bother with something like this. I would do it the way that I know that works. There's lots of other stuff on here. I mean, just for example, this one's weirding me out a little bit right now. It looks like there's some resistors on the gates to these. And if you notice over here, there's 6. And over here, there's 7. 7 little surface mount resistors. Why? Why? Did they just not have enough to fill it? That's something I'm going to explore. I'm going to see what those resistance values are and see if they actually match. Furthermore, why do you have resistors in the first place? Just go straight to the gates. This isn't a multi-frequency amplifier. You don't need to buffer the gates with resistance to get your SWR down. You can just tune it flat out. Same thing over here. 7 resistors on one, 6 on the other. Transformer's got 4 wraps. My intuition tells me that's wrong. So you get these bigger transformers and you try and put more wraps on them, the situation actually gets worse. So you go 1 wrap, 1-to-1, it's about what you would expect. 2 wraps to 1 wrap, you start getting some weird reactance. 3 wraps, you get lots of weird reactance and you have to compensate it out with capacitor. You put a 4th wrap and it's just all over the map. There's so much leakage inductance that the 4th wrap it just kind of kills it. That's my experience anyway. But That's to be determined. That's just one thing that stands out to me that I'm probably going to have to fix. And, yeah. I haven't worked on this other than taking the lid off and staring at it a couple times. But it's going to be a big project. There's a lot to do here. There's a lot to do. This one's going to take me a while because I do this on the weekends, you know. It's not a full-time thing. So far, the worst part about this project has been... Oh, I ran over my dog's paw. So far, the worst part about this project has been cleaning the bench. This is probably the cleanest it's ever been. So that's what's going on. One of the first things I'm going to do is I'm going to take this pallet, because it's still got 2 good FETs in it. I'm going to disconnect all the coaxes and everything and just try and run the pallet by itself and see what it does. If it's reasonable, I'll probably try and fix it. If it's not reasonable, I'm going to tear this thing down to the nuts and bolts and start from scratch. So, that's the plan. Wish me luck. Well, all right. I got the pallet with 2 good FETs in it. I got it plugged in. And I turned it on just a little bit, just to see what would happen. So these wires here, the red and the black, that's powering up the bias. I got that little piece of coax right there. That's looping around. And it is coming from my LP100 low side coupler. So if you see my previous videos, I'm driving it with a signal generator into a little LDMOS preamp, and then that's what I'm driving the amplifier with. The output coax right here is going through the high side on the LP100. It's a dual coupler meter, but you can only read one of them at a time. You got to push the button to switch between the 2 couplers. So I got a bird meter in line, and I'm just seeing if it makes any power at all with a 50-watt slug. So I got it really low on voltage right now just to make sure it doesn't blow up. This is a variable current power supply, so I'm limiting the current as well. And this cable over here is off to my dummy load. Let me put this bad boy on the tripod. Yeah, it looks like a pretty good view. Hopefully you can see everything that's going on. Okay, so one of the first things I did is I turned the bias on and I checked the bias voltage. So that's this multimeter right here. So the one on the left is 1.609. The one on the right, 1.594, 595. So they're biased fairly close. Fairly close. Alright, I'm going to fire up my signal generator here and put some signal into it. So I don't know if you can see that meter on the camera. You can't. There we go. Now you can see the LP100. So this is a low-powered coupler. It's a 250-watt coupler, and it's accurate down to about 0.1 watts. I forget what the gentleman told me when I bought it, but it's fairly accurate, and it reads very low wattages, which is exactly what I want. Alright, so I got my generator on. You can see over here we're putting out a little bit of current already. So that's putting out about 20 watts. What are we drawing? 120 watts in to get 20 watts out. So we're putting in 0.16 watts and we're getting about 35 out on the bird meter. The LP100 saying 38 watts out. And of course, if you can see the SWR, it's perfect because it's going into a dummy load. The input tune is about 2 to 1 SWR. It's not very good. Let's put a bigger slug in there and see what happens. Alright, I got a 1,000-watt slug in there now. Let's up the voltage a little bit. Nice and easy. .15 going in. About 50 coming out. That's a whole lot of watts going in to get not very much out. Okay, so we're running at 48 volts right now. Oh no, got a bad connection over here. You can kind of see it on the spectrum analyzer. Let's see. There's a button over here to freeze this thing. Where's that button? Sweep detect, expand frequency. I haven't used this thing in so long I forget where the button is to just freeze the screen. So these are generating a lot of heat. No. Leo trigger. Let's try that. Come on, give me a connection. There we go. Let's take a minute and look at the spectrum analyzer. We were putting about 50 watts out, something like that, and it's already generating some pretty significant harmonics. So this is our fundamental. On the very left-hand side of the screen starts at 25 megahertz. The very right side stops at 140 megahertz. And this is our primary carrier frequency, so that's at minus 10. This is our second harmonic at minus 40. So what does that make? 35 dB down on the second, 30 dB down on the third. That's not great harmonic performance. Gonna have to do something about that. More concerning is how much heat this palette is generating just to get 50 watts out of it. It looks like the bias is set at about 0.2 amps. Something like that. That meter's not real accurate at low currents. When I want to measure low currents accurately, I have a precision shunt that I use, and I put it in line with the power, and then I'll use this precision multimeter to measure the value on the current shunt. So this is not looking great so far. Harmonics are bad, current draw is very high. I'm about ready to call it a night. Let me think on this, figure out what I want to do with it, and then we'll do it. It's a new day, and I've made some decisions about how I'm going to go forward with this box. One of my biggest concerns here is that there is so much heat on such a small heatsink. So one of these heat sinks is barely adequate for one of these devices running full tilt, let alone two of these devices running full tilt. So there's not an ice cube's chance in hell that one of these heat sinks is going to handle one of these palettes tuned out to the maximum power. The solution is to detune the amplifier so it doesn't put out so much power and quite so much heat. There's another issue regarding heat, and that is the bias circuit on this is not thermally compensated. So I want to see how bad the bias is going to drift and how bad the bias is likely to run away. So what can happen if you don't thermally compensate your bias is that as the device gets warmer, the bias increases. So let's say you set your gates at 2 volts. And let's say, for example, that 2 volts on the gate provides 1 amp of current through the device. As the device warms up, that current is going to increase 2 amps, 3 amps, 4 amps, whatever, even though the gate voltage is the same. So a thermally compensated bias will lower the gate voltage to maintain a constant current regardless of what the temperature is. This pallet does not have that. So it's capable of a thermal runaway. And I want to do a quick experiment with it and see just how bad that can be. So that, I can work with the heatsink and adjust the bias to the right level to where it's never going to thermally run away. That's the goal. So what I've got going on right now is I've got the power supply on 50 volts, and I've got a current shunt in line with the power wires, and I'm going to measure the bias current and see how it drifts as the devices warm up. So I'm probably going to need a temperature probe in here somewhere too. We'll do that in a minute, but I'm just going to play around with the bias. So that shunt over there is 100 millivolts at 50 amps. And our multimeter is plugged into it, so we're reading the millivolts coming off of the current shunt. And every 2 millivolts is 1 amp. So every 0.2 millivolts is 0.1 amps. Hopefully that's easy to understand. Let me get this thing set up and running. I'm probably going to bias the devices at half of an amp each. That's a fair place to start. And then I'll put a temperature probe on it, and we'll watch the drift as the devices warm up. So I'm going to start by reducing one of these all the way down to 0. Actually, I'm going to reduce them both down to 0 so I can know what the... Alright, there we go. So if I'm going for half of an amp, that means I need 1 millivolt per device. So I'm going to adjust this up until my multimeter reads 1 millivolt. Oh, that's touchy. Close enough. And then I'm going to increase the other one until we get a total of 2 millivolts. Oh, very touchy. Wow, look at that. The bias is drifting just with a little bit of heat. So the devices are warm to the touch right now. They're kind of lukewarm. Not hot, but noticeably warmer than everything else. This power supply over here showing 1 amp. But you can see the drift as the temperature of the devices is increasing. Let me find a temperature probe and we'll actually see what that temperature is. Hands are cold. It's not even moving the thermometer. This one will work. There we go. Right between the two devices. (35°C), and we've drifted up 0.2 amps. Alright, just a quick check-in. We're at 74 degrees Celsius. And our bias has gone way up, 2.7 amps. And I'm pretty sure that's the same, approximately the same on the precision current shunt. I want to see what happens when it gets to 100 degrees Celsius. Well, that's 100 degrees. And we have drifted from half an amp per device up to about 2.3 amps per device. That's pretty significant, and that's why we have thermal tracking circuits. That's why my palette uses a thermal tracking circuit. So that temperature probe is right on the heat spreader between the two devices. I think I can live with this. I think I can keep it from going into thermal runaway. Once this palette's all finished, I'm just going to have to set the bias really low. It's like 0.2 amps per device, something like that, and I think it'll be okay. A lot of work ahead of me. I don't know if you guys can tell, but these PCBs, they're just kind of floating there. So there's like one screw here and one screw there, and that's the only thing holding the circuit board to the spreader. I had to break out the macro lens for this. This box has been worked on. I don't know what that is, if it's a broken tap or a chunk of solder or something sticking up in there. These heat spreaders were likely done on a drill press. You can tell because none of the holes are straight. They're all wallered out, not deburred. The plate has not been surfaced, so it's just rough copper extruded bar. This one over here is about the same. This one stripped screw hole, and they had to put a bigger screw, and that bigger screw doesn't even fit the tab on the LDMOS FET. Not much different over here. I think I'm gonna have to remachine this and make some new screw holes, because these screw holes are no bueno. Something else that I found pretty interesting has to do with how these FETs were grounded. Let's see which one of these is the worst. Here, let's take a look at this one. I don't know if you can see that right there, but that looks like an arc mark where the base of the FET wasn't making a good electrical connection, so it was arcing through that point. And pretty much all of these have that. That's a sign that these FETs were not getting sufficient ground. Not at all. So this one is the... Okay. So this one on the left is the one that blew recently. And let's go take a look at this one. This is the one that the palette that we tested earlier. So it's got the arc marks as well. So it's been bothering me this whole time why there's 7 resistors on one FET and 6 on the other. And I just had to flip them over and see what the values were. And it looks like they're all 10 ohms. One of those I can't really read because it's all gooped up with solder. Maybe that'll show on camera? I don't know. But those 6 came out of that side. And then there's 7 of them over here. These came out of the other side. And that on the right is 2 10-ohmers stuck together. I understand the purpose of having resistors on the gates, but I don't understand the purpose of having one gate mismatched from all the other gates. That makes no sense to me. If anybody knows, leave a comment. Let me know why. It looks to me like all but maybe one of the FETs in this box has been blown at one point or another. You can see where the FET blew and took a chunk of the trace off of the PCB. On the gates and on the drains. That can happen if you're careless when you're removing a FET. So if you're taking a good FET out, it it's not that hard to rip the PCB off of there in the process. Um, so that may be the case, but some of these you can see burn marks. That one there, that one there came off when I was working on it. It was just barely hanging on by a thread. That PCB's rough, man. All right, it's about time to start working on these heat sinks and heat spreaders. One of the problems I'm currently facing is that the screw holes are all crooked, stripped out, insufficient, messed up, totally in need of attention. So basically my goal here is just to get this thing mounted properly and correctly and to have a good ground connection between the heat spreader and the PCB. That's going to be a tough one because I was hoping that maybe I could just shift the PCB from one side, shift it over a little bit and drill new holes. Well, there's all these other holes in the way. So it's time for some drastic measures. Basically, the plan here is to cut off this portion of the heat spreader. So everything here is what I'm going to keep, this section here, and all of this I'm going to discard. So I've done a lot of thermal testing in regards to the size of the heat spreader and the thickness and all that good stuff, and heatsink parameters, both in real life testing and what do they call that when you do it on a computer? I don't know. It's a SolidWorks add-on that allows you to thermally simulate all kinds of cool stuff. Takes a crazy powerful computer. It's a fun time. But anyway, through my testing, I have discovered that a heat spreader over, I don't know, what is that? 1 by 3 inches? Anything over that is diminishing returns for a single FET. So a heat spreader this size is not going to be any difference in reality from a heat spreader that's this size. So I'm going to chop it off. We're just going to use this portion, and I'm going to drill some new holes, mount it down to the heat sink in the correct location. But before I do any of this, I have to model it all out so I know where to put the screw holes. I've been metalworking most of my life, so this is my process. I'm going to walk you through it. And we're going to take these over to the Bridgeport, and we're going to drill and mill and do whatever we got to do to get these things mounted up correctly. So my process is with SolidWorks. SolidWorks is like a $5,000 piece of software. But if you wanted to do this at home, there are free alternatives. I think Autodesk has one. I can't remember the name of it, but it's Fusion 360 maybe. Autodesk makes a program, I think it's called Fusion 360, and it's a modeling program very similar to SolidWorks. Of course, it's not as powerful. You get what you pay for, but it would certainly do what we're about to do here. First thing I got to do is model the PCB, or do a drawing of the PCB and all of the different mounting holes. So I'm going to start by sketching up the PCB and all of its mounting holes. And I'll probably fast forward this part so you guys don't have to fast forward the video itself. So the PCB is 116 millimeters on one side. I'm assuming that this PCB was designed in metric because it's very rare that you measure something and it's almost exactly a metric measurement. Like if this was designed in standard, just for example, 116 millimeters is almost 4 9/16, right? Let's see if I can get that in focus. 116 millimeters is almost 4 9/16, but if this was designed in inches, I would expect that number to be more closer to the actual 4.5625, right? So I'm assuming this is all in metric, and I'm going to model it that way. I don't know about you guys, but I am used to working with both standards of measurement. I prefer metric these days, but I don't really care. It's all the same in the end. It's just a number. And I don't have a bigger set of calipers, so we got to measure this. This is about 7 7/8. I don't know what that works out to in metric, but let's see. 7.875 inches. 200 millimeters. Check that out. Let's call it 200. All right, I got to place all these holes and stuff. I won't bore you with the details. If I haven't fast forwarded already, I'll probably do it now. Hey, check that out. So the PCB is definitely designed in metric. I just took some quick measurements, and all of them line up dead nuts with metric numbers. So it's funny. It's got 1/8-inch holes. They're like exactly 1/8 of an inch. So it might be like a 3.2 millimeter clearance hole. Anyway, you guys probably don't care about that stuff. Basically, right now, what I'm doing is I'm just taking all of these hole locations and then putting them onto the model over here. So I've got a couple more holes to do. Then I can work on the heatsink. I've got the FETs aligned to where they need to be on the PCB. And now I got to figure out the screw size and the hole positions for the screws. So it's probably going to be an M3, either a socket head cap screw, or I have these brass Phillips head screws in M3 that might do the trick. But let me check and see what size screw I'm going to use for those. All right, last thing we got to do is make some mounting holes for mounting the copper to the aluminum heatsink. And the existing holes are in no way consistently placed. So I'm just going to make some holes that don't interfere. Probably going to make two around here and then 2 around here. And I'll use whatever screws I have at the shop, but they're probably going to be 1/4-20 countersunk screws like these. Maybe I'll find something different, but that's probably what it's going to be. Whatever countersink screws I got lying around the shop. So. Okay, that's pretty much done. Just got to load the parts in, make sure nothing interferes with anything else. And it all looks pretty good. Alright, I guess I'll start recording again once I'm over there running the machines.